Europe's biggest volcano just slid 4 centimeters in 8 days. And scientists are not talking about the eruptions. They are not talking about the lava. They are talking about something far slower, far quieter, and potentially far more devastating. The entire eastern flank of Mount Etna is racing toward the sea. Not in a million years, right now. And the latest data from 2026 has just revealed a hidden connection that changes everything we thought we understood about this mountain. A connection deep beneath the ocean floor that could turn a slow geological slide into a catastrophic wall of water crossing the entire Mediterranean. The catastrophic potential is clear. 1 million people live on the slopes of this volcano. Millions more line the coasts surrounding it. And here's the part that has researchers genuinely alarmed. This has already happened before. Once. 8,000 years ago. The evidence is still buried in the seafloor. So the question is not whether Mount Etna's flank can collapse. We know it can. The question is, are we already watching it happen in slow motion right now? In April 2016, a team of scientists from the Helmholtz Center for Ocean Research in Kiel, Germany, launched a bold and unprecedented experiment in the waters off Sicily. Their focus was Mount Etna, one of the most active volcanoes on Earth. Specifically, they targeted the unstable eastern flank of the volcano, a massive section of rock long suspected of slowly sliding toward the Ionian Sea. For decades, researchers debated what was driving this motion. Was it magma pressure building beneath the surface, or something else entirely? To find answers, the team deployed 5 acoustic transponders onto the floor of the Ionian Sea. These instruments were carefully positioned above the submarine extension of the fault line separating Etna's unstable flank from its more stable western structure. This marked the first time long-term geodetic monitoring equipment had ever been installed on the seafloor in this region. For the first time, scientists would be able to measure, in real time, whether the base of the volcano was moving beneath the ocean. The mission ran for more than a year, collecting continuous data through July 2017. When researchers analyzed the results, they discovered something extraordinary. During a single 8-day period in May 2017, the seafloor had shifted 4 centimeters. At first glance, 4 centimeters sounds insignificant. But what moved was not a small rock formation. It was an entire volcanic flank, hundreds of cubic kilometers of solid rock. A geological structure that had taken roughly 500,000 years to build shifted as a single mass by 4 centimeters in just 8 days. In geological terms, that is an enormous and deeply unsettling movement. Yet the most groundbreaking revelation was not the amount of displacement, but its pattern. The greatest movement occurred near the coastline, while the least occurred near the summit. This directly contradicted the long-standing theory that magma pressure was forcing the flank outward. If magma were responsible, the summit region should have shown the strongest motion. It did not. This single observation overturned decades of scientific assumption. The data revealed that magma was not the primary driver. Instead, gravity was in control. The southeastern flank of Mount Etna is being pulled steadily seaward by its own immense weight, sliding over soft clay sediments beneath it. The mountain is not being pushed from below. It is slowly, inexorably, collapsing toward the sea. Most people think about Mount Etna as a problem that exists above the ground. Lava flows, ash clouds, eruptions visible from space. But in January 2026, a study published in Science Direct forced researchers to look in an entirely different direction. Not up at the volcano. Down. Into the ocean floor beneath it. The study integrated geological, geochemical, geodetic, and archaeological data collected from Etna's eastern flank over multiple decades. And it reached a conclusion that substantially changes the way scientists understand this entire system. The sliding faults responsible for the flank's instability are not operating in isolation. They are directly connected to the hydrothermal vents on the floor of the Ionian Sea. Here is how that connection works. As the southeastern flank slides, it continuously fractures and shifts the rock beneath it. That constant movement increases the permeability of the geological substrate, essentially cracking open pathways through the earth. And through those pathways, hot mineral-rich fluids from deep inside the planet rise upward and discharge onto the ocean floor. The fault movement is not just destabilizing the volcano, it is sustaining an entire underwater hydrothermal ecosystem. What makes this finding genuinely alarming is the word scientists use to describe the relationship between these two systems. Coupled, the tectonic instability and the hydrothermal activity do not simply coexist. They depend on each other. One feeds the other, which means that any significant change in the pace of the sliding has the potential to disrupt the hydrothermal system in ways that are still extremely difficult to model or predict. And then there is the broader tectonic context that cannot be ignored. Mount Etna does not sit on stable, quiet ground. It stands on the edge of the Calabrian subduction zone, one of the most geologically complex and active regions in the entire Mediterranean. The faults crossing the floor of the Ionian Sea surrounding it are, according to local volcanologists, independently unpredictable and potentially more hazardous than the volcano itself. These are the same faults, the same system, all of it connected, all of it active, and all of it moving. On the first day of January 2026, Mount Etna opened the new year in a way nobody anticipated. A flank eruption began on the eastern slope of the volcano at an elevation of 2,100 meters, directly inside the Valle del Bove. The same horseshoe-shaped depression that exists precisely because this flank has collapsed before. The same zone that monitoring data had identified as the most unstable section of the entire structure. The eruption did not begin at the summit. It began in the scar. Within 24 hours, the fissure advanced further down the valley, reaching 1,420 meters of elevation by January 2nd. Ash clouds rose into the airspace above eastern Sicily, forcing aviation authorities to issue warnings across the surrounding region. On the surface, the response was measured. The National Institute of Geophysics and Volcanology in Italy assessed that the lava flow developing inside the Valle del Bove was reducing immediate risk to inhabited areas by channeling volcanic material away from populated slopes. No mass evacuations, no catastrophic destruction. But the eruption itself was not the story. The eruption was a signal, and what it was signaling was this. Pressurized magma was actively moving through Etna's internal system at the start of 2026, and the research already established that magma intrusions are the primary accelerant of flank sliding. Every time magma rises, friction along the fault decreases, and the southeastern flank moves faster. The January eruption was not just a volcanic event. It was confirmation that the engine driving the slide had just been given more fuel. Then, 10 days later, the Ionian Sea responded. On January 10th, a magnitude 5.3 earthquake struck the ocean floor off the coast of Syracuse, shaking eastern Sicily and rattling communities along the coast. Scientists were careful to clarify that this event had no direct connection to Etna's volcanic activity. It originated from independent movement along the submerged faults of the Ionian Sea. But that clarification carries its own warning. The faults beneath the ocean are not waiting for the volcano. They are moving on their own timeline, and both systems are active simultaneously. 8,000 years ago, the eastern flank of Mount Etna collapsed. Not gradually, not over centuries. It collapsed, and what followed was a tsunami that did not stop at the Sicilian coastline. It crossed the entire Mediterranean Sea and reached the shores of what is today the coastline of Israel, more than 1,600 kilometers away. The wave did not discriminate between countries, coastlines, or civilizations. It simply traveled until the ocean absorbed it. This is not a theory. It is not a worst-case scenario constructed by scientists trying to justify research funding. It is documented geology, preserved in marine sediments on the ocean floor, and recorded in the growth rings of ancient trees. The evidence has been sitting in the earth for 8 millennia, waiting to be read. And what it tells us is straightforward and uncomfortable. This mountain has already done this once. The conditions that produced that collapse exist today, and the flank is still moving. The scale of what a repeat event would mean in 2026 is almost difficult to process. Approximately 1 million people currently live on the slopes of Mount Etna. Millions more inhabit the coastal communities surrounding the Ionian Sea. The ports, the cities, the tourist infrastructure built along these shores exist with almost no physical buffer between them and open water. A tsunami generated by a significant flank collapse would not offer hours of warning. It would offer minutes. Researcher Marilia Urlaub, who led the Helmholtz Center study, was direct when asked about the risk of sudden acceleration. Her answer was not reassuring, but it was honest. It could happen in 10 years. It could happen in 100. It could happen in 100,000. Science does not currently have the tools to narrow that window with any meaningful precision. That uncertainty is not a reason for dismissal. It is the entire point. The 8,000-year-old tsunami was not predicted either. The communities in its path had no monitoring systems, no warning protocols, and no understanding of what the mountain above them was capable of. The question worth sitting with is a simple one. How different are we, really? Mount Etna is not being ignored. If anything, it is one of the most watched pieces of ground on the planet. Dozens of seismic sensors are embedded across the volcano's slopes. High-precision GPS units track surface movement in real time. Satellites equipped with InSAR imaging technology measure ground deformation from orbit, detecting shifts of just a few millimeters across the entire volcanic structure. And beneath the Ionian Sea, underwater transponders continue the work that the Helmholtz team began in 2016, listening for movement in the fault systems that no surface instrument can reach. All of it runs continuously, 24 hours a day, every day of the year. If the southeastern flank begins to accelerate significantly, the monitoring network is designed to detect it. Mediterranean tsunami warning systems are already in place for coastal communities across the region. The infrastructure of awareness exists. That matters, and it should not be minimized. But the data coming out of 2026 is forcing scientists to confront something that monitoring alone cannot resolve. The connection between the flank sliding, the seismicity of the Ionian Sea, and the submarine hydrothermal vents is far more tightly integrated than researchers understood even 5 years ago. These are not 3 separate problems being tracked by 3 separate teams. They are one system. And the behavior of one component directly influences the stability of the others in ways that current models still cannot fully capture. There is also the question of what accelerating flank movement would mean for the deep-sea ecosystems sustained by those hydrothermal vents. Entire communities of organisms exist on the floor of the Ionian Sea, dependent on the mineral-rich fluid discharge that the sliding faults make possible. A significant disruption to that system would not just be a geological event. It would cascade through an ecosystem that exists nowhere else in precisely this form. The honest scientific position, held by the researchers closest to this data, is this: detection is possible, prediction is not. The monitoring systems can tell us when something is changing. They cannot tell us how far that change will go, or how fast, or what threshold separates a measurable acceleration from an irreversible one. The people who live on the slopes of Mount Etna are not unaware of the volcano above them. They have grown up with eruptions. They have watched lava flows creep toward their villages and recede. They have learned to read the mountain's moods in a way that outsiders cannot fully appreciate. But the threat that the 2026 data describes is not the threat they have been preparing for. It is quieter, slower, and it does not announce itself with fire and ash before it becomes catastrophic. Early warning infrastructure exists across the Mediterranean, and it is more sophisticated than it was even a decade ago. But the speed at which a significant flank collapse could generate a tsunami places enormous pressure on the interval between detection and response. Minutes are not hours. Evacuation plans designed for gradual emergencies do not automatically translate to scenarios where the danger is already in the water before the sirens activate. The January 2026 eruption and the magnitude 5.3 earthquake that followed 10 days later were not catastrophic events in isolation, but their proximity in time matters. 2 separate components of the same interconnected system activated within days of each other. Researchers flagged the coming months as a critical observation window precisely because of that sequence, not because disaster is imminent, because the system is demonstrably awake. The broader implication extends well beyond Sicily. Mount Etna is not a regional curiosity. It is a window into how volcanic, tectonic, and oceanic systems behave when they are stressed simultaneously. The lessons being learned here about coupled geological systems, about the limits of predictive modeling, and about the gap between monitoring capability and true forecast precision apply to volcanic coastal environments across the entire planet. What scientists want the public to understand is not that catastrophe is coming tomorrow. It is that awareness is not the same as alarmism. Understanding the real nature of this threat, its scale, its interconnections, and its historical precedent is the only foundation on which meaningful preparedness can be built. The mountain is not waiting for the conversation to catch up. It is already moving. The people who live on the slopes of Mount Etna are not unaware of the volcano above them. They have grown up with eruptions. They have watched lava flows creep toward their villages, sometimes slow enough to film, sometimes fast enough to redraw maps. They have swept ash from balconies, listened to windows rattle in the night, and returned to daily life once the smoke thinned. Over generations, they have learned to read the mountain's moods in ways satellites and sensors still struggle to replicate. But the threat described in the 2026 data is not the kind that glows red against the sky. It is not a spectacle of fountains and fire. It is quieter, slower, and far more structural. And it does not announce itself with drama before it becomes catastrophic. Across the Mediterranean, early warning systems are more advanced than at any point in history. Seismic networks triangulate tremors in seconds. GPS stations measure ground deformation down to millimeters. Ocean buoys register subtle shifts in sea level. Yet even with this technological web in place, a significant flank collapse presents a brutal timing problem. The physics are unforgiving. If a massive section of Etna's unstable eastern flank were to slide into the Ionian Sea, the displacement of water could generate a tsunami within minutes. Minutes are not hours. Detection is not evacuation. Emergency frameworks designed for lava flows or ashfall assume time. Time to analyze. Time to decide. Time to move. A landslide-triggered wave compresses that timeline into a narrow and unforgiving window where hesitation becomes consequence. The January 2026 eruption, followed 10 days later by a magnitude 5.3 earthquake, did not devastate Sicily. In isolation, neither event qualifies as extraordinary for a volcano as active as Etna. But proximity matters in geology. Two components of a deeply interconnected system activated in rapid succession. Magma movement alters internal pressures. Seismic shifts redistribute stress along faults and within the volcanic edifice itself. Researchers identified the months following that sequence as a critical observation period, not because disaster is inevitable, but because the system demonstrated coherence. It moved as one organism rather than isolated parts. It signaled wakefulness. What unfolds on Etna's slopes is not solely Sicily's concern. Mount Etna is one of the most instrumented volcanoes on Earth, precisely because it serves as a living laboratory. The interaction between volcanic activity, tectonic stress, and marine instability offers rare insight into coupled geological systems. These lessons extend to coastal volcanoes worldwide, from the Canary Islands to Indonesia, where dense populations live within reach of both lava and sea. Monitoring has improved, modeling has improved, but precision forecasting remains elusive. Scientists are not warning of apocalypse tomorrow. They are emphasizing a distinction the public often blurs. Awareness is not alarmism. Recognizing structural vulnerability is not the same as predicting imminent collapse. Preparedness begins with understanding scale, history, and interconnection, not panic. The mountain does not pause for reassurance. Beneath villages and vineyards, beneath roads and harbors, it continues its slow mechanical adjustments. It is already moving. 4 centimeters in 8 days. That is where this story began, and it is the number worth returning to now. Not because it is the largest measurement in this story. It is not. But because it captures something essential about the nature of this threat. It is small enough to dismiss and significant enough to change everything, depending entirely on whether you understand what is behind it. What is behind it is 500,000 years of accumulated volcanic rock, sitting on a tilted layer of soft clay sediments, pulled by gravity toward an ocean floor, threaded with active fault lines and hydrothermal vents that an entire deep-sea ecosystem depends on for survival. What is behind it is a prehistoric tsunami that crossed 1,600 kilometers of open water and carved its signature into marine sediments that scientists are still reading today. What is behind it is the January 2026 eruption inside the most unstable zone on the volcano, followed 10 days later by a magnitude 5.3 earthquake from faults that operate on their own independent timeline. None of these pieces are speculation. All of them are documented. All of them are connected. and all of them point toward the same conclusion that the researchers closest to this data have been carefully, methodically, and urgently trying to communicate. This is not a future problem. It is a present one. The sliding has not stopped. The faults are not resting. The system is not dormant. It is active, it is coupled, and it is being monitored by some of the most sophisticated geological instruments ever deployed, by scientists who are the first to admit that monitoring and predicting are not the same thing. Mount Etna has been moving for 500,000 years. It moved before the first human settlement appeared on its slopes. It moved through every eruption, every earthquake, every civilization that built itself in its shadow. It will continue moving, regardless of what we do or do not understand about it. The monitoring is in place. The data is being collected. The warnings are being issued. The only question that remains is the most important one. Is anyone listening?